differentiation. The following slides show my process in this process. The process is, of course, a circular thing. During this project, I moved back and forth between ideas. This helped me make new discoveries and create relationships between things. This presentation, however, attempts to show my process in a linear fashion. My idea started with the concept of worlds within worlds. An analogy of this would be Russian dolls. Each doll is its own separate piece, but collectively they make up one body. Every time you open one of the dolls, another doll similar in appearance appears. The only thing that is different is the size of each doll. The way I interpreted the title of this project, Museum in Drag, was Museum of Contradiction. So I explained how I could contradict the idea of the Russian doll. I made a sculptural representation of this idea. Each time you open up one of the objects, a new one appears. The other interesting thing about this is scale. Without a reference, one object could be the same size as the previous. From here, I wanted to diagram how this contradiction of worlds within worlds could be applied. I decided to explore different volumes that could be used. I looked at how these different volumes could imply or define space. The light gray shows loosely implied space. The darker gray shows the more well-defined spaces. I then took the volumes that I had diagrammed and built a diagrammatic model using them. I placed each of the volumes within a frame. I saw how they interacted both with each other and with the extent of the frame. They were placed at varying heights and were attached differently to create relationships. Next, I took the volumes I studied and placed them in the context of the building. The interesting thing that I saw had to do with circulation. By placing individual spaces through an additive process, a unique circulation path is created. Instead of a linear circulation, a more complex circulation that changes direction several times is created. The red line shows the circulation. I then explored the mathematical concept of fractal geometry. I felt like this idea related to my original idea of worlds within worlds. A fractal is a rough geometric shape that can be split into parts, with each part representing the whole. Because they are self-similar, fractals are believed to be infinite in detail. They are interesting in terms of scale because they can be zoomed in and out of and look the same. Fractals are considered to be the geometry of nature. They can be found in many different places. Some include plant growth, lightning, clouds, coastlines, and snowflakes. The fascination with the geometry of nature has long existed in man. Fractal-like geometry has been used in art and architecture for a long time. After studying fractals, I diagrammed the way that they worked. The images on the left show how to follow the laws of fractals. Each shape is broken down into smaller, self-similar shapes. Since my goal is to contradict these laws, I then explored how to do the opposite of the nature of fractals, as seen in the images on the right. To further develop my idea, I began to research other mathematical concepts and theories. The next one I looked at was the golden ratio, or golden rectangle. Discovered by the Greeks, it is an aesthetically pleasing rectangle with sides in a 1 to 1.618 ratio. They first took a square and then, using a radius from a side's midpoint to an opposite corner, made an arc and extended the square to the arc's end. The Greeks later discovered that the rectangle that they added was also a golden rectangle. Although it was coined by the Greeks, the golden ratio actually exists in nature. The human body is full of examples of golden proportions. The distance from navel to forehead and the human face are some examples. The rectangle has also been found to exist in many famous works of art and architecture. Classical architecture and Renaissance art are some examples. After researching, I looked at how the golden rectangle worked diagrammatically. I took a rectangle and then divided it in half several times. Each one of these subdivisions had a ratio of 1 to 1.618. I then diagrammed how to divide the rectangle in half several times in order to contradict the ratio. I also explored how to break the rectangle up. The third mathematical concept that I looked at was Fibonacci sequences. The sequence starts with 0 and 1, and each remaining number is the sum of the previous two. The interesting thing about this sequence is its relation to the golden ratio. As the sequence grows, the ratio between two adjacent numbers comes closer to the golden ratio. Like fractals, Fibonacci sequences are abundantly found in nature. This type of growth pattern produces a spiral shape. This shape can be found in things like nautilus shells and flowers. It is also found in the growth of human lungs. The sequence is also used to predict the population growth of certain species. To apply the Fibonacci sequence, I thought of using numbers as intervals of length or distance. I first explored how to do this in plan by separating sections of usable space with areas of circulation. I then did the same in section, using the sequence of numbers as the height of usable spaces. To contradict the sequence, I used it backwards, starting with 13 and moving down to 1 and 0. The math which I researched is also the program for the Museum of Complex Math. I'm sure we've all wondered at one point or another when we were going to use the math we were taught. The truth is, some topics you may never see again, but most of them are utilized in one way or another. The experience in the museum would broaden one's knowledge and enable them to see where math is applied every day. After researching, I needed to come up with a way to make all the theories work together and contradict the rules set up by these theories. To contradict fractals, I would use varying types of volumetric spaces that seem to not be related, except for the fact that they are put together. Each of these spaces would either be a rectangle of golden proportions or a square. These spaces would operate at vertical heights, moving opposite the Fibonacci sequence. For circulation, I drew inspiration from N.C. Escher's paintings of stairs. I saw a complex system of making circulation change direction over and over. I came up with a system that was not a circulation path, but rather a web of circulation between separate spaces. This allows a person to move freely and to experience what they want to in their own way. To show this complex circulation, I let it influence the facade of the building. The circulation is shown on 3 sides as well as the roof using an incision of glass. This shows circulation 2-dimensionally on each side. However, when this design is extruded through the building, something happens. Where the paths cross is where each piece of circulation lies. The design also shows the backwards Fibonacci curve. The idea is that a person would come in knowing little or nothing about complex math. They would learn about ideas and theories as they see where they can be applied in everyday lives. They would see that everything, no matter how chaotic it seems, has an order based on mathematics. As they travel down the spaces in the museum, they will know more about how math orders our world and will leave with an understanding of the system.